Welcome back to the deep dive. Today we are taking concepts that traditionally never really get invited to the same party. We're talking ancient Chinese medicine and the fundamental structure of the cosmos.
Right. And we're going to see what happens when we sort of force them into conversation. It's quite a mix.
Exactly. We're plunging into a highly speculative, I should say, yet incredibly detailed hypothesis. It's all about the physical reality of acupuncture meridians.
That's right. For millennia, these meridians, well, they've been seen as these abstract energy pathways, right? Conduits for what traditional Chinese medicine calls qi. And, they've largely been dismissed by modern conventional science, mainly because they just don't map onto any known anatomical structures, no nerves, no blood vessels that line up.
Nothing concrete you can point to on a standard diagram.
Precisely. But our source today, this is based on the research of an independent researcher, J. Alfred. His work proposes that these pathways are not abstract at all, not just energy.
Okay, so our mission today is really to investigate this framework thoroughly. It suggests these traditional pathways are actually associated with ephemeral plasma-like structures.
Ephemeral meaning short-lived, fleeting.
Exactly. In essence, think extremely weak, constantly dissipating electrical currents.
And here is the disruptive part, the real kicker. The mechanism that's hypothesized to sustain these currents, the process that repeatedly makes them sort of blink into existence.
Yeah.
It draws heavily on dark matter physics and a specific phenomenon the author calls dark ionization.
Wow, okay. Dark matter. So the core question driving this deep dive is, can the cutting edge of plasma physics and dark matter research finally provide that scientific bridge?
A bridge between this ancient concept of internal energy pathways and, well, contemporary biophysical science.
It feels like we need to go deep into the dark sector, ironically, to find the physical basis for something that's always been seen as intangible.
Okay, let's unpack this fascinating proposal. Because really, to understand the meridians in this model, we first need to set the stage with the underlying physics. We need to talk about the author's foundational dark plasma hypothesis.
All right, so the first step in this model requires us to, frankly, radically rethink the composition of our own planet.
Yeah, this is foundational.
J. Alfred posits that dark matter isn't just some, wispy halo way out there around galaxies. Near ordinary matter, like right here near Earth, it's proposed to exist as a complex, self-interacting plasma.
And that leads us directly to this, well, kind of mind-bending concept of parallel dark Earths.
Parallel dark Earths, okay.
We often think of dark matter as passive, maybe inert, but here it's highly structured. The hypothesis suggests a significant chunk of the dark matter near Earth exists in this complex plasma state.
Not just particles, but a plasma.
Exactly, forming massive structures. The author called them dark plasmaspheres or dark Earths. And critically, these aren't separate things floating nearby. They are gravitationally coupled to our ordinary matter Earth. They co-rotate with it. They entirely permeate our planet, like ghosts within the machine almost.
That sounds absolutely wild. I mean, truly science fiction territory. But the author anchors it back to a very concrete historical problem in physics, something called mass conflation.
Yes, mass conflation. Think about the classic Newtonian gravity calculations, figuring out the mass of the Earth. For centuries, scientists used gravitational measurements to do that.
Standard practice.
Right. But those measurements, they're only sensitive to the total mass present. They can't distinguish between types of matter. So they measured the sum of all the ordinary matter, the rocks, the water, the core, plus any dark matter component that was co-rotating with us.
Oh, okay. So those historical estimates of Earth's mass we all learned in school, they already baked in the dark matter component without anyone realizing it.
That's the argument. It effectively obscured the presence of these massive, permeating, co-rotating dark Earths. The math worked out for the total gravity, but the physical constituents were misunderstood. We didn't know what we were weighing.
So we were essentially blind to the dark matter inside Earth because we just attributed all its gravitational pull to the ordinary matter we could see or infer.
Precisely. I mean, if every planet and the sun itself had significant amounts of relatively dense dark matter right there in their cores, the resulting gravitational calculations would still seem consistent with the combined mass. We just wouldn't know any better from gravity alone.
Which makes the recent findings on atmospheric neutrino oscillations so crucial, right? This is how modern science has started to actually peek inside and maybe detect this unseen mass inside our planet.
That's exactly right. Scientists have been using these huge detectors, like the ice cube detector down in Antarctica and the Super Kamiokande experiment in Japan, They analyze neutrinos,
Yeah.
specifically atmospheric neutrinos. And these oscillations, the way neutrinos change type as they travel through matter, give us subtle clues about the density and composition of whatever they pass through, including the Earth's deep interior.
And the data coming out of those experiments is, well, highly suggestive, isn't it? What are the key numbers supporting dark matter inside Earth?
The analysis points towards really significant mass percentages, even at the 1 sigma statistical level, which, indicates a strong likelihood, not just noise. Researchers estimate that approximately 20% of the entire Earth's mass,
20%.
or if you look just at the core, about 30% of the core's mass, might actually be composed of dark matter.
20 to 30%. That is not a negligible dusting. That's revolutionary, really. It completely challenges the standard models of how solar systems form, which usually assume planets are almost purely ordinary matter.
It's a huge amount. And it's certainly more than enough mass, this vast unseen foundation, to support the gravitational influence of a series of these, let's say, tenuous dark Earths the author proposes. It provides the necessary energetic background for the whole mechanism.
And that critical mechanism is the dark ionization process. This is where it gets really active. This is the central action where the ordinary matter of our bodies, or anything else, and the dark matter of these coupled dark Earths start to interact.
Yes, dark ionization. The basic principle is collision physics. Think particles bumping into each other.
Okay.
When dark matter particles, components of these structured dark Earths, collide with the atoms of ordinary matter particles, say, in your body, the force of that collision can sometimes be enough to knock out electrons and protons from those ordinary atoms. It's a kinetic interaction. And that action ionizes the ordinary matter, generating ordinary plasma.
So it's like a subatomic game of billiards where a dark matter cue ball knocks electrons off ordinary atoms.
A pretty good analogy, yeah. And this leads to a kind of chain reaction driven by density and speed.
Okay, walk us through that sequence. How does density lead to more plasma?
Right. It begins with the density of the dark plasma itself. If a dark plasma body, or maybe just a specific filamentary region within it, increases its particle density, just more dark particles packed into a given volume,
Okay.
that inherently raises the collision rate with ordinary matter. More particles, more bumps.
Makes sense.
Then, that increased density affects something called the plasma frequency.
Which is the rate the plasma particles sort of oscillate together collectively?
Exactly. Plasma frequency is directly proportional to particle density. So higher density means higher plasma frequency. The particles oscillate faster.
Okay.
And that increased motion, that higher speed of oscillation, then causes the collision rate to increase even further. It feeds back on itself.
A positive feedback loop. More density, faster wiggling, more collisions, more ionization, maybe even more density locally.
Potentially, yes. It intensifies the dark ionization process in these localized areas.
Now let's tackle the most maybe counterintuitive part of this, temperature. Plasma usually makes us think of stars, incredible heat. But this source specifically refers to cold plasma. Why isn't this process generating scorching temperatures?
This is absolutely critical. It solves one of the biggest hurdles for any kind of bioplasma idea. During these collisions, the resulting ordinary plasma is cold, meaning non-thermal, and it's because of the huge difference in particle size and mass.
Okay.
Think about the particles involved. You have ordinary protons, dark protons maybe, and tiny little electrons. The protons, being much larger and heavier, have a significantly bigger cross-section. Think of it as a bigger target area for collisions compared to the electrons.
So the big, heavy protons are much more likely to get hit in these collisions.
Much more likely. They collide more frequently, and when they collide, they share energy and cool down quickly. The electrons, being tiny and light, they don't get hit as often, so they can remain hot, zipping around energetically.
Right.
But, and this is the key, the overall mass density of the resulting ordinary plasma is overwhelmingly dominated by those heavy, numerous cold protons.
So if you measured the average temperature based on the mass, it would register as cold, even if some tiny electrons are momentarily very hot.
That's it. It's like having, I don't know, a handful of red-hot grains of sand thrown into a swimming pool full of ice cubes. The average temperature of the pool is still going to be near freezing, despite those few hot grains.
That's a great analogy. So the average temperature of this ordinary plasma created by dark ionization is much, much cooler, similar to the cold plasma scientists make in labs.
Yes, exactly. Those can be near room temperature or just slightly warmer. Nothing like the thousands of degrees needed for thermal plasma, like in the sun. This avoids the whole scorching the body problem.
Okay, that makes sense. So once this ordinary cold plasma is generated, energy gets released when the displaced electrons fall back to lower energy states or recombine with ions. What are the outputs? What should we be looking for along these meridian pathways if this is happening?
There are 5 key outputs listed that result from this dark ionization process. First, heat. Even though the plasma is cold on average by mass, the interaction still generates some detectable thermal energy.
Okay.
This would likely manifest as weak infrared radiation, maybe microwaves, very low-level stuff on the electromagnetic spectrum.
Second output?
Light. This is potentially crucial for visibility, if it's strong enough. The ordinary plasma emits ordinary photons as electrons drop energy levels. This could make the plasma envelope momentarily luminous.
So maybe a very faint glow, or perhaps just a subtle shimmer, like heat haze, or even a shadowy effect, right?
Exactly. Faint glowing or maybe a shadowy disturbance. Very subtle. Third, radiation. The process generates a broader electromagnetic spectrum beyond just heat and visible light.
Like what?
At low energy, you'd expect radio waves and infrared, as mentioned. The source does note, though, that rarely, if the collisions are particularly energetic, the process might emit higher energy radiation, things like ultraviolet or maybe even X-rays.
Which could be harmful to tissues, presumably.
Potentially, yes, if it were sustained or intense, which is not expected to be the norm here. Fourth output, electromagnetic fields. This is almost a given.
Because you have charged particles moving.
Right. Moving charges create magnetic fields, and charge separations create electric fields. But the movement isn't random here. The hypothesis is that the underlying dark plasma structure oscillates naturally, periodically.
Ah, so it's not just constant collisions, but rhythmic ones.
That's the idea. It collides with ordinary matter in a predictable, periodic way. And this periodic influence causes the density of the generated ordinary plasma to fluctuate, increase, and decrease cyclically.
Okay.
And that cyclical density modulation generates a pulsating electromagnetic field, and it would radiate pulsating electromagnetic waves.
That's really important. It implies the meridians wouldn't be static channels, but fundamentally pulsed or oscillating phenomena.
Precisely. Finally, the fifth output, electricity. The ionization process itself displaces ordinary electrons. This generates weak, transient electrical currents and localized electrical fields.
Which sounds exactly like the kind of subtle electrical phenomena that have been measured around acupuncture points for decades.
It aligns very well, yes. But this entire output network, all these effects, they're inherently short-lived. And this brings us right back to the biggest challenge this hypothesis has to overcome, the dissipation problem.
Right. You mentioned ordinary plasma just doesn't last at Earth temperatures.
Exactly. At the surface of the Earth and inside a human body, the average temperature is around 288 Kelvin, which is about 15 degrees Celsius or 59 Fahrenheit. Pretty cool from a plasma perspective.
And at that low temperature?
Standard elementary particles in ordinary plasma, the ions and electrons, they rush to recombine back into neutral atoms almost instantly. Plasma wants to neutralize itself very quickly in these conditions.
So any ordinary cold plasma structure generated randomly on Earth or in the body would just vanish. Poof. In a tiny fraction of a second.
Absolutely. So for these meridian pathways to exist even fleetingly, even as these blinking structures, they must be continuously generated and regenerated by some external ongoing source. They can't sustain themselves.
Okay, so that external source, the dark matter interaction, is constantly relighting the fuse, so to speak.
That's the core idea, which links directly into our third foundational concept, the visibility of this cold plasma envelope. If these filaments are indeed cold plasma, how they appear, or maybe more importantly, why they usually don't appear, depends entirely on these frequency dynamics.
Right, you mentioned this relates to plasma frequency.
Yes, it's all about the relationship between the plasma frequency of the filament itself and the frequency of ambient electromagnetic waves hitting it, like visible light. That relationship dictates how the plasma interacts with light. Does it act like a mirror, a lens, or something that absorbs?
It's like tuning a radio, you said. The radio only really interacts strongly with the signal if it's tuned to the right frequency.
That's a perfect analogy. Let's break down the 3 states of visibility described in the source material. First state, when the plasma frequency is greater than the ambient light frequency.
So the internal oscillations of the plasma are happening faster than the frequency of the light waves hitting it.
In that case, the plasma body reflects that ambient light. It basically acts like a metallic mirror. It would shine brightly.
So in this state, the filament or structure would be highly visible, appearing maybe solid, reflective.
Potentially, yes, if conditions were right. Second state, if the plasma frequency is less than the ambient light frequency.
Oscillating slower than the light waves.
Right. If the frequency is lower, the light tends to pass right through, relatively unhindered. The plasma acts more like a refractive lens in this case. It might bend the light slightly, but primarily it becomes transparent.
So effectively, the filament just disappears from view. We wouldn't see it.
Exactly. And the third state, which is perhaps the most intriguing, where the plasma frequency equals the ambient light frequency, the frequencies match.
That sounds like resonance.
It is. Resonance occurs. The frequencies align perfectly, and the light energy is absorbed by the plasma filament. It takes the energy in.
And when something absorbs light, it appears dark or shadowy.
Correct. So in this resonant state, the filament would appear dark. And this mechanism, this cycle of potentially shining, then disappearing, then appearing dark, could explain this idea of scintillation, or the blinking nature of the meridian that the dark plasma model proposes. It's constantly changing its interaction with light.
Okay, the theoretical framework is laid out. We have dark Earths permeating us, their localized interactions generating these continuously reionizing, ephemeral, cold plasma filaments that can flicker in and out of visibility. Now, we absolutely have to connect this, well, frankly, quite abstract physics to what we actually observe or think we observe in the body. Hashtag #TAG2, the electrical nature of acupuncture meridians.
Yes, this connection is vital. Is there any actual evidence that points towards electricity in these meridians? And the idea that meridians conduct something electrical or subtle, well, it isn't new. Historical findings have consistently pointed in this direction, even if they couldn't pin down what was conducting.
Like the early work from scientists at Jiaotong University in Shanghai, I remember reading about that. They used sophisticated electrical mapping gear, didn't they?
They did. And they demonstrated that the energy, whatever it was, flowing through these ancient pathways exhibited measurable properties of an electric current. They could track it electrically.
And then there was the pioneering work of Dr. Robert Becker in the U.S. He was quite controversial but influential.
Very much so. In his own experimental observations, Becker proposed that the acupuncture meridians were a fundamental part of the body's bioelectric control system. Specifically, he thought they conducted direct current, or DC.
DC like a battery, not the AC of nerves.
Right. And this scientific work is kind of reinforced by a lot of anecdotal evidence. You hear reports from healers, people who claim enhanced sensitivity, even accounts from near-death experiences. They often describe this subtle circulating energy as feeling electrical, but subtle. Distinctly different from, say, the harsh bioelectricity of a nerve firing or the heart beating.
So a long history of hints. This all leads up to the more contemporary scientific evidence that seems to support a distinct electrical nature for these pathways. The most cited findings seem to involve resistance and capacitance, right?
That's probably the most robust line of evidence,
Yeah.
the low impedance and high capacitance finding. A systematic review, pooling data from many studies, was done by Ahn and colleagues.
Okay.
And they found that quite consistently, acupuncture points and the linear paths connecting them, the meridians tend to exhibit lower electrical resistance or impedance.
Easier for current to flow.
Yes. And at the same time, higher capacitance compared to the surrounding control tissue.
Meaning they can store electrical charge better, like a capacitor.
Exactly. So less resistance to flow, better ability to hold charge. Those are characteristic electrical properties.
Now, hang on. I can almost hear a skeptical doctor or physiologist yelling right now, low resistance. That's just because acupuncture points are often over areas with more blood vessels, or maybe thinner skin, or it's the fascia. How does this plasma theory specifically address the possibility that simple anatomy is the cause?
That's a crucial point, and we have to address the conventional explanations head-on. But let's first state the plasma connection clearly. Low electrical resistance is a defining characteristic of plasma. Plasma is an excellent conductor of electricity. So if the meridian is a channel of plasma, it would inherently allow continuous current flow with low resistance. The model explains low impedance naturally.
Okay, but let's tackle those anatomical counterarguments first. What are the standard explanations trying to tie these electrical properties back to known structures?
The standard medical models suggest, as you said, that low resistance at these specific points might just be due to mundane anatomical features. Things like increased vascularization, more blood vessels mean a more conductive fluid, high density of nerve endings in that area, or, the most popular hypothesis these days, intersections or pathways within the connective tissue matrix, the fascia.
The fascia argument is quite prominent now.
It is. The idea is that fascia could act as a sort of semiconductive network, guiding ionic currents through the body. Other explanations include just having thinner epidermal layers at those points, or maybe higher hydration levels locally, both of which would reduce skin resistance measurements.
Okay, those all sound plausible on the surface. Yet J. Alfred's hypothesis seems to gain its strength precisely because those conventional explanations face significant, persistent critiques, especially regarding anatomical consistency.
Absolutely. That's the main weakness of the conventional views. The major criticism is anatomical consistency. Study after study has failed to consistently map the 14 major meridians onto known anatomical structures like specific nerves, blood vessels, or lymphatic pathways. They just don't line up neatly across individuals or even sometimes within the same individual over time.
And the fascia argument.
The fascia argument, while attractive, because fascia is everywhere, remains largely speculative. There's a lack of consistent histological evidence showing a distinct, organized fascial structure that runs precisely along only the traditional meridian lines and nowhere else. Fascia is more like a web.
It doesn't form neat channels in the way meridians are depicted.
Not usually, no. Furthermore, while things like the ionic conduction hypothesis, the idea that signals are carried by ions drifting through tissue fluid, are plausible electrically,
Yeah, you mentioned that aligns with plasma-like conduction.
it does align with ion movement being key. But those mechanisms aren't necessarily exclusive to acupuncture points. You can stimulate tissue almost anywhere and induce some local ionic currents. It doesn't fully explain the specificity and networked nature of the meridian system.
So conventional biology kind of struggles to pin down a consistent anatomical basis for this measurable, reproducible electrical phenomenon. But low resistance is perfectly characteristic of plasma.
Yes. And that ionic conduction hypothesis research from around 2020 is important too. It really bolsters the idea that whatever is carrying the signal, it involves ion drift and diffusion currents. It fits the isothermal transient ionic current theory.
Meaning conduction based on free ions, not electrons in wires like nerves use for action potential.
Exactly. It supports the idea that the signal conductor is ion-based, largely independent of standard neural signaling or just bulk cellular bioelectricity.
Yeah.
It smells like plasma, even if it doesn't screen plasma definitively on its own.
Okay, so the conductivity studies confirm something unique and electrical is happening along these lines. And the source suggests the only way to sustain this kind of phenomenon in the body's environment is via this dark ionization model. But to really make that case, we need to tackle why ordinary biological plasma just can't be the answer. #tech3, historical bioplasma research, why ordinary plasma is unlikely.
Right. This section is critical because it basically explains why Alfred's dark matter model is even necessary.
Uh-huh.
Before anyone thought of linking this to dark matter, many scientists, especially in the Soviet era, tried to define bioplasma, a self-contained living plasma within the body.
Okay.
And they consistently ran into, well, let's call them 5 fundamental scientific walls. 5 reasons why ordinary plasma just doesn't work in biology.
Let's start with that Russian bioplasma hypothesis from the 1970s. What were they proposing?
Scientists like Ionization and Sedak, they proposed that living organisms actually contained a substantial amount of bioplasma. They thought it consisted of ions, free electrons, and free protons.
The basic ingredients of plasma.
Yes. And they believed this stuff was concentrated in areas like the brain and the spinal cord. They thought it was maybe produced by mitochondria, the powerhouses of the cell, and perhaps even absorbed from the environment.
Okay, wait. Right there, that absorption idea runs smack into the dissipation problem we just discussed.
Immediately, at 288 Kelvin, ordinary plasma recombines almost instantly. It's just not physically plausible that a substantial amount of ordinary bioplasma could be absorbed from the air or ground and maintain any kind of permanence inside the wet, relatively cool body.
Or even be synthesized by mitochondria and stay stable for more than a blink. The body is basically a plasma extinguisher, not a container.
Exactly. That's wall number 1.
Yeah.
Wall number 2 is the energy gap problem.
Mhm.
Ionizing atoms, ripping electrons off, requires a massive amount of energy, far, far beyond what basic cellular biology produces locally.
How big is the gap?
Well, Ionization suggested maybe bioplasma was a cold plasma made of highly structured collective excitations in biological semiconductors. Things like dipole waves or maybe plasma-like modes. But these kinds of collective biological excitations operate at the millielectron volt scale. Millielectron volt is tiny, 1,000th of an electron volt.
And for comparison, what energy level do you actually need to ionize atoms and create stable plasma?
To get sustained ionization of ordinary matter, you typically need energies ranging from the electron volt EV scale up to the kilo-electron-volt keV scale.
So that's a factor of 1,000 or even 1,000,000 times greater than what these biological collective excitations provide.
Exactly. There's this vast energy gap. The body simply doesn't run hot enough or have strong enough local fields to constantly pull electrons off atoms and sustain a plasma state through its own internal processes.
Okay, insurmountable energy gap. What's the third issue?
The third issue relates to the body's environment itself. We can call it the aqueous dissipation problem.
Water again.
Water again, and density. Biological systems are dense, they're aqueous, mostly water, and they're highly regulated chemically. They're designed to maintain stability, not host plasma. Water especially is a killer for plasma. Any free energy, like that in a plasma, gets rapidly dissipated through molecular collisions, through interactions with the hydration shells around ions. Energy just gets soaked up and spread out instantly. Plus, to generate plasma in the first place, you need extreme electric field strengths to ionize water or tissue.
How strong?
Orders of magnitude stronger than the strongest fields we typically find in the body, which are around cell membranes and mitochondria, maybe 70 to 150 millivolts across a tiny distance. It's just way too weak for bulk ionization.
Okay, so the wet, dense environment is inherently anti-plasma. Roadblock 4.
Roadblock 4 was pointed out by researchers Quickenden and Tilbury back in 1986. It's about hydrodynamic control. This is more of a conceptual barrier, distinguishing a simple soup of charged particles from true plasma.
What's the distinction?
For something to qualify as true plasma, the collective movements of its charged particles must be governed primarily by electrical and magnetic forces, the long-range forces that dominate plasma dynamics in space, for instance, not by the movement of the surrounding fluid, which is hydrodynamic behavior, like currents in water.
And in the body?
In the body, ion movement is almost entirely governed by fluid dynamics, by concentration gradients, by diffusion. It's hydrodynamics, not electrodynamics, that rules.
So even if the body has lots of free ions floating around, if they're just being carried along by fluid flow, it doesn't count as true plasma.
According to Quickenden and Tilbury, no. They argued that conventional semiconductors, which some models tried to use for bioplasma, only exhibit true plasma behavior near absolute zero temperature, or if they are perfectly pure and free from contaminants, which the biological system emphatically is not.
Okay. And the fifth hurdle, this one seems the most obvious. The temperature barrier.
Yeah, this is the big one. Ordinary plasma, the kind we understand from astrophysics or fusion research, requires thousands of degrees Kelvin, typically 4,000 to 10,000 K.
Which translates to?
That's roughly 3,700 to 9,700 degrees Celsius, or 6,700 to 17,500 degrees Fahrenheit. Temperatures that would instantly scorch, vaporize, and utterly destroy any biological tissue.
Even a few hundred degrees Celsius would be immediately fatal.
Absolutely. So a thermal bioplasma, a hot one, is completely impossible within a living organism.
Okay, so summing up, ordinary plasma dissipates instantly, needs way too much energy to form, gets quenched by water, isn't governed by EM forces in the body, and would vaporize us anyway. The scientific consensus seems pretty clear.
It is. A substantial, quasi-neutral, ordinary bioplasma body simply cannot exist with any permanence on Earth or in an Earth-based organism.
These 5 barriers are just insurmountable for conventional biology and physics.
And that is precisely where the dark plasma advantage comes in. J. Alfred's hypothesis, using dark matter, is specifically engineered to sidestep these 5 fatal flaws.
Exactly. Let's see how. The temperature problem, solved by weak interaction.
How so? The dark plasma structure itself, the underlying engine from the dark Earth, is proposed to interact only weakly with our ordinary matter body. So even if that dark plasma were incredibly hot in its own dark matter terms, we wouldn't feel it under normal circumstances. Its heat is largely irrelevant to our ordinary matter physiology.
Okay, so the source of the energy is thermally isolated from us. What about the persistence problem? Ordinary plasma vanishes instantly. How does the dark plasma itself survive Earth's low temperatures?
The theory here is that dark matter particles likely have a much weaker effective electric charge compared to ordinary matter protons and electrons.
Weaker charge means?
Weaker electromagnetic attraction. So the dark plasma ions and electrons don't rush to recombine nearly as quickly, especially at low temperatures. It can exist as a long-lived, stable plasma structure within its own dark plasmasphere environment.
Okay, so the dark plasma persists and interacts weakly enough not to fry us.
Correct. And the conclusion here is pretty definitive within this framework. The only way to have a quasi-neutral plasma structure associated with the human body that persists over time is through some kind of external continuous generation mechanism.
And the dark ionization process provides exactly that, an ongoing external energy source tapping the persistent dark plasma to constantly sustain these ephemeral, low-density, ordinary, cold plasma filaments within us.
That's the proposed solution. Hashtag tag tag 4V, dark plasma model of acupuncture meridians. The synthesis.
All right, we've established the theoretical engine dark ionization powered by persistent dark plasma. We've seen how it potentially solves the temperature and persistence problems. Now we need to combine this with the observed electrical phenomena of the meridians. This synthesis seems to start with a really out there idea, a symbiotic link.
Yeah, this is where the hypothesis takes a significant leap. The authors suggest that humans, perhaps over evolutionary time, may have formed a kind of endosymbiotic relationship with a type of dark plasma life form.
A life form made of dark plasma.
That's the proposal. A life form inhabiting this dark Earth structure. And its dark plasma body is theorized to be coupled to, or maybe even fused with, our ordinary matter body. And there's a proposed interface layer, a dark plasma envelope, acting as a port between the two.
Wow, okay. That's a lot to take in. Assuming that coupling exists, there must be structure within that dark plasma body to explain the specific lines of the meridians. That brings us to filament formation.
Right. Plasma physics isn't just about uniform clouds of charge. It's highly geometric. We see this in labs. Experiments on complex plasma, or dusty plasma, show they often naturally organize themselves into high-density filamentary structures, like columns or strings or wires, often forming between areas of charge separation.
Like mini lightning bolts, almost, but stable.
Sort of, yeah. The theory posits that the coupled dark plasma body likewise contains an organized grid or network of these high-density dark plasma filaments. And these filaments represent regions where the dark matter particle density is vastly higher than the surrounding ambient dark matter.
Okay, so there's an underlying dark matter scaffold. And these higher density dark filaments are the literal meridian genesis point. They are the template.
That's the core of the meridian model. Because these dark filaments have vastly greater particle density compared to the ambient dark matter around them, they significantly increase the likelihood of dark matter or ordinary matter collisions, specifically along those filament pathways.
Ah, so the ionization doesn't happen randomly throughout the body, but is concentrated along the lines of these dense dark filaments.
Precisely. This intense, localized collision rate initiates the dark ionization process predominantly along the contours traced by the dark filaments.
So the meridians we might detect electrically aren't structures in the ordinary body, but rather the effects of an underlying invisible template on the ordinary body.
Exactly. The result is these localized, weak, ordinary, cold plasma filaments forming along those contours. And the weak electrical currents generated would naturally follow the architecture of the underlying dark filaments, which is why, the theory suggests, they appear independent of the body's known anatomical networks like nerves or blood vessels. They're following a different map.
A dark matter map. This leads us back to the crucial characteristic of this network. It must be ephemeral. We know the ordinary plasma dissipates almost instantly. How is the appearance of persistence maintained? How can we even measure it?
It's maintained by that constant cycling, the constant regeneration. It's sustained by repeated and periodic reionization events. The persistence isn't because the ordinary plasma itself is long-lived, it isn't. It's because the underlying dark plasma structure keeps rhythmically triggering new ionization events along the same path, causing the ordinary plasma filaments to rapidly manifest and dissipate over and over again.
Like a strobe light illuminating a path. The path seems continuous, but it's actually a series of flashes.
An excellent analogy. They're continuously being created and destroyed in very quick succession.
And this rapid cycling could explain that scintillation or blinking effect we talked about earlier. How might that look or feel or be measured?
Well, imagine a very, very faint electrical sign that's constantly flickering, sometimes brighter, sometimes dimmer, sometimes off. The density modulation happening in the underlying dark plasma body would cause the resulting ordinary plasma filament's own plasma frequency to oscillate or fluctuate.
Right.
And as we established back in Section 9, that plasma frequency determines its visibility, how it interacts with light. So as its frequency shifts, the filament might alternatively shine brightly, reflecting light, then become dark, absorbing light, and then become transparent, refracting light and disappearing.
A shimmering, almost holographic electrical outline that repeatedly blinks into existence and then vanishes within the ordinary matter body.
That's the picture painted by the model. And along these flickering filaments, the electrical characteristics we can measure, the low impedance and high capacitance found in studies, are simply the measurable properties of these ephemeral, weak plasma currents during their brief moments of existence.
So the acupuncture meridian system, according to this model, has a kind of dual character. It acts as an interface.
Yes, it's characterized as these weak, ephemeral streams of ordinary cold plasma, an ordinary weak current network within the body. But this network serves as the visible, or at least electrically detectable, imprint and the functional interface of a deeper, more persistent, dark plasma current network.
The meridian we interact with is just the tip of the iceberg, the observable consequence of a hidden dark matter infrastructure coupled to us.
That's the idea. And this radical shift in understanding, if true, would have profound physiological and therapeutic implications, especially regarding how the body operates and heals.
What's the first major implication?
The first is bioelectric modulation. The weak, cold plasma generated along these meridian lines, ephemeral as it is, could still interact with and subtly modulate the body's own inherent bioelectric field.
The body's background electrical blueprint.
Exactly. And this bioelectric field isn't just a byproduct of cells doing their thing. There's fascinating research, particularly by scientists like Michael Levin, showing that this bioelectric field acts as a critical informational layer. It's like a master controller,
Controlling what?
guiding fundamental processes like morphogenesis, how tissues and organs develop their shape and structure, and also regeneration after injury. The body's electrical fields contain spatial information.
So if this dark plasma-generated trace is influencing the body's main bioelectric field, it means the meridians could actually be influencing how the body plans its structure, responds to injury, or even develops disease.
That's the profound implication. We know that anomalous voltage gradients in the bioelectric field often correlate with the disease states, like cancer. By introducing a tiny electrical pulse, like with an acupuncture needle, or maybe influencing a sustained current via this plasma trace, you could potentially gently nudge the body's bioelectric field. And that nudge could, in turn, influence disease progression or structural organization and healing.
Okay, that's huge. What's the second major implication?
The second is the potential inherent healing properties of the generated cold plasma itself.
Not just its electrical influence, but the plasma's direct effects.
Yes, and this is where the theory connects quite nicely with modern clinical research that has nothing to do with acupuncture initially. Ordinary cold plasma, the kind made in labs, is actually being used therapeutically today.
For what?
It's known to be very effective at killing bacteria, so it's used for decontamination. And remarkably, it also seems to promote human skin wound healing. Studies show it can enhance cell proliferation and improve blood flow locally.
So the cold plasma generated by this hypothetical dark ionization process would naturally possess those same therapeutic properties.
That's the reasoning. The author speculates that this locally generated cold plasma might even be utilized by these proposed coupled dark plasma life forms for processes like detoxification or healing within the ordinary body. It's providing an internal source of therapeutic cold plasma.
Let's try to connect this back to traditional Chinese concepts. They talk a lot about qi, balance, yin and yang. Is there an equivalent concept in this plasma model? The paper mentions quasi-neutrality.
Yes, quasi-neutrality is key here. The core of the model really revolves around plasma stability. Quasi-neutrality is the state where overall the positive and negative charges within the plasma balance out perfectly.
Yeah.
There's no large-scale net charge.
Okay.
And this state, quasi-neutrality, is a defining characteristic of a stable, well-formed plasma body. Interestingly, it's also the very hallmark of homeostasis, or physiological stability, in life forms.
Balance. So the question the author seems to be posing is, could acupuncture treatment, maybe through the mechanical stimulation of these ephemeral plasma traces with a needle, be fundamentally attempting to achieve or restore quasi-neutrality in that ordinary bioplasma?
That's a fascinating way to frame it. If the system becomes non-neutral, meaning there's an imbalance of positive and negative charges locally, it would produce non-neutral currents. And these unbalanced currents could potentially disrupt the normal operation of the body's bioelectric field, perhaps leading to dysfunction or disease symptoms.
So the ancient goal of balancing qi might translate in modern biophysical terms to restoring charge balance within these flickering plasma filaments.
The potential translation, yes.
Yeah.
A very interesting one.
And finally, just to round out the model, we should note that while this paper focuses heavily on acupuncture as the most common way we interact with the system, the author suggests certain traditional practices might go beyond acupuncture.
Yes. Practices like high-level Qigong, or certain forms of yoga, particularly those that explicitly focus on cultivating and circulating internal energy, or qi. Right. These are theorized to potentially engage the underlying dark plasma body more directly, more consciously, than standard needle therapy might.
Implying that advanced practitioners might actually be trained, perhaps unconsciously, to modulate the dark ionization process itself, influencing the strength, structure, or flow within the underlying dark filaments through intention or physiological control.
That's the intriguing suggestion. It opens up a whole other level of potential interaction. Hashtag VP suggested experiments.
Okay, this is the crucial pivot point. We've explored the theory, the potential implications. It's fascinating speculative stuff. Now we move from that to hard science. How could we actually test this? What are the practical steps J. Alfred proposes to try and verify or falsify this hypothesis?
Right, the experiments. These need to be designed very carefully, obviously. They generally require specific, high-resolution diagnostic methods capable of looking for precisely the kind of signals the theory predicts. Faint, fluctuating pulsed signals that are not tied to known biorhythms like heartbeat or breathing.
Before we get into the specific technologies, the author stresses a prerequisite for making these experiments work effectively: the role of meditators.
Yes, this is considered essential. Any really conclusive experiment, the paper argues, must be performed using highly experienced, advanced meditators, specifically citing Qigong practitioners, alongside a rigorously matched control group of non-meditators.
Why are the meditators so critical here? Why not just test average people?
The reasoning goes back to that idea we just touched on. These individuals, through years of training, may possess a developed ability, whether through focused intent, deep physiological relaxation, or some other mechanism, to consciously modulate the dark ionization process.
They might be able to turn up the volume on these plasma filaments.
Or at least change the pattern or strength in a controlled way. This modulation, if it exists, would amplify the resulting ordinary plasma filaments, making the emitted electrical and electromagnetic signals stronger, clearer, and therefore easier to detect above the background biological noise.
So the experiment would need to carefully correlate any detected signals with the practitioner's mental state, like comparing signals during deep meditation focused on moving energy versus periods of normal rest.
Exactly. Meticulous correlation between the detected signal strengths and pattern and the practitioner's reported state or scheduled meditation periods focusing on internal energy circulation would be key.
Okay, assuming we have our groups, let's detail the proposed diagnostic methods. What's the first approach? Trying for visual confirmation.
Yes, the first is optical emission and spectroscopy, basically looking for light. This would involve using extremely sensitive optical imaging equipment. Think high-resolution charge-coupled device, CCD cameras, maybe photomultiplier tubes, things that can detect incredibly faint light.
And what are they looking for?
They'd be searching for faint emission lines, specific frequencies of light that are characteristic of cold plasma, and they'd be looking specifically along the known paths of traditional meridian lines in human tissue.
And timing would be critical?
Yes. The test would need to be performed specifically during activities believed to increase meridian activity, like active Qigong practice, or perhaps during an acupuncture session itself. And since the theory predicts heat output too,
Right, infrared and microwaves.
researchers should simultaneously employ sensitive detectors for weak infrared and microwave signals emanating from the same meridian pathways, correlating them with any optical signals.
Okay, looking for the light and heat signature. What's the second proposed test? This one sounds more interactive. Bioelectric field modulation.
This one tests the predicted interactivity. If these meridians are plasma channels, they should respond to external electromagnetic fields. So the experiment would involve carefully applying external fields, maybe low-frequency pulsed electromagnetic fields, PMF, for example, to specific meridian points, or along segments of a meridian.
And what's the expected outcome if the theory is right?
If there are plasma currents, these external fields should interact with them, modulate them, maybe induce resonances. That interaction should then produce measurable physiological responses, perhaps localized pulses in skin conductivity, changes in blood flow, or even systemic shifts in the body's overall bioelectric field patterns that can be tracked with other sensors.
So basically, you poke the hypothesized plasma with an EM field and see if it jiggles in a way that normal tissue wouldn't.
That's a good way to put it, yes. Does it respond uniquely to electromagnetic stimulation along those lines?
Third test. This involves mapping electrical properties with very high precision, high-resolution electrical conductivity mapping.
Right. This likely requires sophisticated technology like electrical impedance tomography, often called EI.
How does EIT work?
EIT typically involves placing an array of electrodes on the skin surface. Small, harmless electrical currents are passed between pairs of electrodes, and voltage differences are measured at all the other electrodes. By analyzing how the currents flow, a computer can reconstruct a 3D map of the electrical conductivity and permittivity inside the tissue volume.
Okay, so you get a detailed electrical picture of the inside. How would you use it here?
Researchers would use EIT to map conductivity, specifically along the traditional meridian pathways. But they wouldn't just be looking for static low resistance. The crucial search is for minute fluctuations in conductivity.
Fluctuations that match the blinking plasma idea.
Exactly. Fluctuations that are highly organized, maybe patterned or pulsed, and critically, fluctuations that are statistically distinct from known biological rhythms like the heartbeat, breathing artifacts, or muscle twitches. And you'd need to compare these signals meticulously with control regions of the body that don't correspond to any known meridians.
Looking for a unique, flickering electrical signature along the meridian lines. Fourth test. Detecting the magnetic signature. This sounds like it needs incredibly sensitive gear. Magnetic field detection using SQUIRTES.
Yes, SQUIRT stands for Superconducting Quantum Interference Device. This is probably the most technologically demanding test.
Why SQUIRTS?
Because SQUIRT are the most sensitive magnetometers known to exist. They can detect incredibly minute magnetic fields that are many orders of magnitude weaker than the Earth's own magnetic field, or even the fields generated by the human heart or brain, typically measured by MEG or MCG.
And the hypothesis is that these weak plasma currents would generate equally weak magnetic fields.
Correct. Since any electrical current generates a magnetic field, SQUIRT will be positioned very carefully to try and detect the minute, likely pulsing magnetic fields generated by these hypothesized weak plasma currents flowing along the meridian channels.
And again, the key is the pattern.
Yes. Detecting any field isn't enough. The focus must be on finding organized magnetic patterns that fluctuate and pulse in a recognizable manner, clearly separate from biological noise or external environmental magnetic interference. You're looking for a tiny, coherent magnetic beat specific to the meridian lines.
A magnetic whisper, almost.
Magnetic whisper is a good description, yes. SQUIRTs are necessary because the current strength is predicted to be extremely weak, given the ephemeral nature of the ordinary plasma.
Okay. And finally, the fifth suggested experiment involves simulating the proposed mechanism directly, the effect of cold plasma treatment.
This experiment basically asks, if the meridians work via cold plasma, what happens if we apply cold plasma artificially? It aims to replicate the therapeutic effect using controlled laboratory methods.
How would that work?
Researchers would use devices that generate laboratory-produced cold plasma, the kind used in medicine already, created without any dark matter involved. They would apply controlled beams of this cold plasma directly onto traditional meridian points and maybe non-meridian control points.
And then monitor the effects.
It's exactly. Monitor the resulting tissue responses very carefully. Look for localized effects known to be associated with cold plasma, like enhanced blood flow, reduced inflammation, maybe accelerated tissue healing rates. And also look for any systemic effects, changes in the body's overall bioelectric field balance or other physiological markers.
And the crucial comparison.
Comparing the effects seen when applying plasma to meridian points versus non-meridian points. And also comparing the effects of applied cold plasma to the effects seen during a standard needle acupuncture session targeting the same points. If the applied cold plasma produces similar or perhaps even amplify therapeutic results specifically along traditional lines, it would strongly support the hypothesis that the natural process underlying acupuncture is also plasma-mediated.
Okay. These 5 experiments, optical detection, EM field modulation, EIT conductivity mapping, SQUIRT magnetic detection, and direct cold plasma application, they provide a pretty comprehensive roadmap. A way to scientifically investigate whether these ancient meridian lines might actually be physical imprints of ordinary cold plasma, constantly regenerated by a deeper layer of dark plasma interaction. #tag conclusion.
So looking back at the whole hypothesis, the real profound strength of this framework proposed by J. Alfred lies in its potential ability to resolve those major physical problems, the ones that really defeated all the earlier historical attempts to explain bioplasma.
Right. You're talking mainly about those fundamental barriers of temperature and persistence.
Precisely. The temperature problem, the fact that ordinary plasma would vaporize us, is potentially overcome because the primary engine, the underlying dark plasma structure, is theorized to interact only weakly with our ordinary biomolecular body. Its own dark heat just isn't effectively transferred to us.
And the persistence problem, the fact that ordinary plasma vanishes instantly at body temperature, how is that solved again?
It's solved because the ephemeral ordinary plasma isn't required to be stable itself. It's constantly being regenerated, reionized by the rhythmic, periodic collisions driven by the underlying, much more stable, long-lived dark plasma structure. The dark plasma provides the continuous energy input.
So it neatly sidesteps the need for ordinary plasma to be stable in an unstable environment.
Exactly. And the significance of this, well, it really goes far beyond just explaining acupuncture, doesn't it?
Absolutely. If these suggested experimental methods, particularly the high-tech ones using squeads and electrical impedance tomography, if they actually reveal consistent, organized phenomena along these traditional pathways.
And phenomena characteristic of plasma, like those specific fluctuations, patterned pulses, distinct from other biorhythms.
Yeah, if that's found, it would rewrite entire chapters of physiology, wouldn't it? It would be revolutionary.
It really would. It would establish perhaps the first truly tangible, scientifically grounded bridge between these ancient medical concepts of subtle energy pathways and modern biophysical science. Confirmation would fundamentally redefine our understanding of human anatomy and physiology.
It could open up entirely new avenues for understanding health and disease, maybe leading to completely new therapeutic strategies focused on modulating these bioelectric and plasma interactions.
Definitely new ways to diagnose, new ways to treat based on this interface layer.
It certainly makes you look at yourself differently, not just as a biochemical machine running on familiar neural electricity and hormones and fluids.
But potentially as a composite system, operating on all those known factors, yes, but also intimately linked to and perhaps constantly being modulated by these incredibly subtle, short-lived, dark matter-induced plasma currents. Currents that are constantly blinking in and out of existence just beneath the surface of our perceived physical world.
Absolutely incredible to think about. That was definitely a deep dive into the very fabric of our being, suggesting that maybe a whole component of our functional anatomy has been essentially invisible to us.
And perhaps a final thought for you to consider. If our physical well-being, our homeostasis, our health, is somehow fundamentally tied to achieving or maintaining this state of quasi-neutrality within these ephemeral plasma structures.
If our health depends on balancing the charges in these flickering dark matter imprints,
Then what does that truly imply about the fundamental, ongoing connection between the ordinary matter world we see and interact with every day and the unseen, pervasive dark matter that surrounds us and, according to this, permeates us? Our health might ultimately be defined not just by what's inside our ordinary bodies, but by our balance and interaction with the dark half of our reality.